Hello. So I want to start my talk with a trivia question. I have a contract with two functions here. The question is, which one is more gas efficient? Here we have a contract C which has a dynamic array, ARR, which is initialized to something. And we have two functions A and B, which tries to compute the sum of this array. And the first function A is that A is how you would write this in any other language. You have a for loop, and then you iterate over the array using this for loop, and you have a variable sum that would compute the partial sum at any point I, and at the end you have the complete sum. But now let's look at B. In B, you start with copying the array from storage to memory, and then you do the same calculation over the memory copy instead of the storage. There is this solidity dictum that you have to start by copying all the storage stuff into memory, and that's what we are doing in B. And the question is, which one is more efficient, A or B? It's B? A. I mean, let's just say 20 elements. Is it? So the answer is it B or A? Okay, let's say B. But which one is more readable? What do you think? Okay, A is readable. That we can agree on. I won't answer this right now, but but that kind of motivates why we need an optimizer. We need an optimizer because we want to write simple code, and we want it to be as gas efficient as possible. But before I get into what is the optimizer, we have to understand how the compilation works at a very high level. So you start with the parsing. So you have the Solidity code, which gets parsed into an abstract syntax tree. We call it an AST. It's a tree because it resembles like a tree data structure. So let's say you have a contract, and which is a node, and the child nodes would be, let's say, the functions, the variables, etc. And after that, we perform some analysis on this AST that we just parsed. And this is where all the type checking, type errors, like all sort of errors from the compiler comes from. And once you have the analysis step, we can now do the code generation. So Solidity has two different code generators. The first one is called the legacy code gen because it was the very first one to be implemented. So this basically translates the AST into EVM bytecode directly. There is some caveat here. I'll get into it later. And once we have the EVM bytecode, we can perform some bytecode-based optimizations. This is an optimizer step. And the second one is called the intermediate representation, where we translate the AST directly into EUL. You can enable the flags ---- viaIR or viaIR : true, depending on how you compile. On CLI, you use the ---- viaIR. On standard JSON, which most of the tools use, they use viaIR : true. So what this does is that it translates the AST into a somewhat higher level language called EUL. You are probably familiar with EUL. It's very similar to the assembly syntax. And now you can perform the EUL optimizations. So once we have the optimized EUL code, you can translate this code into EVM bytecode. And once you have the EVM bytecode, you can again do bytecode-based optimizations on it. So there is one caveat in the legacy part, which is we still use EUL for some part of the code generation, even in the legacy code generator. So my talk would be mostly about the optimizations, and in particular, about the UL optimization. So let's start with the bytecode-based optimization. How does it work? So it usually works across basic blocks. A basic block is a sequence of assembly instructions that does not have any complicated control flow. And once we have that, we could try to, let's say, evaluate some of these expressions. For example, if you see an add of a comma b, where a and b are just constants, you could just evaluate it. That's a very simple example of what the bytecode-based optimizer can do. You can find more in a rule list. Once you download the slides, you can click on the links. But the big downside is that it cannot really perform complex optimizations. Of course, you could always engineer it in such a way that it can perform significantly more complicated optimizations. But we also don't want to do it because of some engineering reasons that we will get into later. So where does the bytecode-based optimizer fail? So here is a very simple example. You have a function f that would just return the value a times 2. So remember that we have a rule called, we have a rule that translates a multiplication by 2 into a shift, a left shift by just one bit. Why do we do it? Because multiplication costs 5 gas, whereas shift costs 3 gas. So we save 2 gas by doing this. So if you look at this function's bytecode and look at the basic block, what we get here is a jump test followed by a push 2 and a mul opcode. And unfortunately, we cannot use the rule in this case because the value a is outside the basic block. And shift requires like swapping the arguments. And as I said before, you can, of course, fix this by doing more complicated analysis. But yeah, I will get to later why we don't want to do this. So this somewhat motivates why we need a more complex optimizer, which is the UL optimizer. So basically, it can perform significantly more complicated optimizations. So in the same example, if you look at an approximation of the IR generated by this function, it would look like this function f here. And once we have this IR, we can easily optimize the multiplication into a shift. So if you use the minus via IR codegen and the optimizer, this optimization would actually get applied. Whereas in the legacy, it doesn't, even though we have a rule for it. So in general, what can UL do better? There are some very minor issues that people complain about since years. All of these issues do not even exist in the UL optimizer. Very simple things like removing redundant division by 0 checks if you know that the divisor is non-zero, and it can inline significantly better. Inlining looks like a very trivial thing to do, but turns out that it has a huge effect in gas savings. And another thing is that the UL to EVM code transformation can manage stack significantly better. More details about this can be, you can learn more about it in Daniel's talk, which is right after me. And also, pack structs are much better optimized in the UL codegen and its corresponding optimizer. And you always hear like trivial things like use x not equal to 0 instead of x greater than 0. These things are completely redundant in the UL-based codegen and optimizer. And speaking of the design, UL has a set of small and independent steps that can be executed in a sequence. So it's much easier to build these optimization rules, and it's much easier to reason about the correctness. Now, going back to the question from the beginning of the talk. So you have the same array here. And if you look at the translated UL, it would look something like this. So you have a you have a variable sum, which is initialized to 0, and you have a for loop. So for loops are well-defined opcodes. Sorry, it's not opcode. For loops are well-defined in the UL. So the for loop in UL would look like this. So you have you initialize I to 0, and then the loop condition would be checking if I is less than s0. What is s0 anyway? So s0 is the length of the array, assuming that the array length is stored at storage slot 0. And then we have the post condition, which is the I++. So of course, you can already see that we have an extra check for overflow for I, which is actually redundant, but this is how the code is generated right now. And then inside the loop, you can look at the array value I getting accessed by nsload. And then there is an overflow check for sum plus equal to array of I. How can we optimize this better? What do you think? Yes, but there is a significantly, yeah, go on. Yeah, exactly. So there is the s-log of 0, which the less than of I, comma, s-log of 0 check. The s-log of 0 gets executed at every loop iteration. But as you can see here, none of the storage gets written inside the body. So this s-log of 0 is an invariant in this loop. So we could just like take it outside the loop. So the optimized code would look something like this. So the length is outside the loop, and it saves around 100 gas for every loop iteration. Of course, there are a couple of more optimizations possible here. The overflow checks for the I can be removed. The compiler doesn't do that right now, but we do have some future plans to do that. But let's just say that, yeah, this is how the optimized UL would look like for this code. And in the other case, we start by copying the array into memory, which is completely redundant and has memory overhead. And to go back to the answer, in the legacy codegen, yes, B is cheaper. But in the viaIR codegen, the very simple implementation is actually cheaper. So hopefully I was able to convince you why you should use viaIR and UL Optimizer. Now I want to add some random notes about benchmarking. So when you try to optimize your contract, especially smaller optimization, you have to always benchmark it. And when I say benchmark, you should try to write a contract that does things in a certain way and try to write the same thing in a different way and try to check which one has lower gas. But one caveat here is that the function dispatch can affect the gas. So what is a function dispatch anyway? So if you have a contract with a couple of external functions, When I say external, it can also be public. The point is that it's externally callable. So here you have 3 functions, A, B, C, in the which are externally callable. And the dispatch would look something like this. I have a contract C bytecode, which tries to emulate the dispatch in Solidity. So you have a fallback function, and the fallback function would check for the message or signature. The selector for A, I mean, there is the, at first you check for the selector for A, and if it's matching, you would call A. After that, you would check for the selector for B, and if it matches, you call B. And after that, C. So what you can see here is that if you want to call C, there is some overhead for the check for A and B. So if you are benchmarking, you should try to create contract with only a single function, and then benchmark, look at the gas for the 2 different contracts. And the other thing you can do is to look for the diffs of assembly as well as the optimized IR. I've noticed people looking at the diffs for binary, but the problem with the binary is that it's unreadable. But the compiler actually generates a much more readable assembly output, which you can get by using the --ASM option. Or even better, you can try to use the optimized IR and then look at the diffs for the optimized version. So it turns out that codeball.org now has Solidity support. So if you want a quick online tool to see how the compiler generated code or look at the diffs, you can use that. So what next in the optimizer? Okay. So the general idea, as I mentioned before, is that intuitive code should also be optimal. In the near short term, what we want to do is improve the inlining heuristics. It's very surprising how much you can do with just inlining. In the past, we had some restrictions around how much we can inline, mostly because the more you inline, the more the stack, the more the stack code gets messier. So because the EVM only allows you to access the first 16 or so stack slots, if you had highly inlined code, you were more likely to get into a stack too deep issue. But since Daniel has this new implementation for translating from YUL to EVM, we can get around many of these stack too deep issues easily. And even when we can't get around the stack too deep issues, we can always lift them into memory. So this means that we can continue improving our inlining heuristics without any of the stack issues. We were also thinking about doing significantly more complicated optimizations that require some kind of symbolic reasoning. So here is the same example from before. And we noticed that there was this redundant check for overflow in I++. So these checks can pretty much be only done if you have some sort of symbolic analysis in the EVM, sorry, in the compiler. Of course, you could always use an external tool like Z3, which is an assembly checker, but we don't really want to do that. We don't want to rely on an external tool to generate the code. At the same time, it also introduces some problems like non-determinism, which is very annoying if you want to properly verify contracts. And one big challenge for the optimizer is to optimize memory usage. This is something that the compiler currently struggles with. Yeah, now I want to dedicate one slide about the safety and some of the engineering decisions we made. So in general, the compiler is written with correctness in mind. So we want to be able to write some Solidity code, and the key point of the compiler is that it should generate correct EVM code, semantically correct EVM code. So we want to make the bytecode level optimizer as simple as possible because it's extremely complicated to work at the bytecode level. And if we can do it at UL, which is significantly easier to reason about and decrease the complexity, we should keep it at that. And other than that, we generally fuzz the compiler very well. There are a couple of interesting aspects here. The first aspect is that we built a lot of assertions in the code generation step, as well as the optimizer. So what happens is, and these assertions stay in the compiler. So even if you are compiling in a release mode compiler, these assertions would still be there. And whenever these assertions fail, the compiler would crash. This is especially interesting for fuzzing. We have a team member, Bhargava, who exclusively works on fuzzing. The fuzzer can generate random Solidity programs and try to see if these invariants can be broken. This is also true for the optimizer. You can generate UL code and try to see if these invariants inside the UL optimizer can be broken. More interestingly, because we have two different code generators, one for legacy and one for UL, you could try to generate random Solidity programs and try to see if both of this code generator would produce semantically equivalent code. You could just generate random call data and call this contracts and see if the state is the same. Again, you could repeat the same thing with optimized versus unoptimized code gen. And fuzzing has been very, very successful in finding bugs before we make a release. And all of this are continuously fuzzed as well. There is also some external fuzzing efforts from academia. Alex is one such contributor. And we also try to formally verify some step whenever we can. So the team has written a minimal version of an EVM symbolic execution engine. Whenever we have a simplification rule, for example, the trivial one, add of x comma 0 equal to x, we can try to write a proof in this symbolic framework that these two expressions are actually equivalent in the EVM. And we try to do that especially for these steps that involve arithmetic operations. If you click at the link here, you could see how it's done. Of course, we do try to write handwritten proofs whenever possible, and regular engineering practices such as code reviews. Also, I want to highlight that we actually don't know any issues that happen on chain due to a compiler bug. So hopefully, I was able to convince you about the quality of the optimizer and also why you should use it. So we want to encourage you to try the newer versions, especially the viaIR pipeline. Yeah, that's it.
Hi. Here. Thanks for the presentation. I have two quick questions. The first one is, in your example, you said the YOL optimizer kind of do the S-load trick for us. So you cache it locally, so we don't have to write cache storage values in a loop anymore. Does that mean it applies to general just storage as well, or it's only in the for loop? So it's do we still have to cache all the storage value if we want to use it more than once, or it's all handled by the YOL optimizer?
Yeah, the key point I want to add here is that the optimizer is inferring at the optimizer step that there is no writes here, and that's why you can cache it. So the optimizer has to infer this information from the code you generated. So if there is any code that can violate this condition, then the optimizer cannot do it. For example, if there is a call here, then the optimizer cannot prove that there was no invalidation of this value at slot 0. But maybe the programmer can know that, okay, this call would never violate this slot. So in such cases, yes, you have to cache, but again, I would recommend you to always benchmark, always try to look at the code generated as well.
Okay, so like, just try to make sure I get it right. So in most cases, if it's pretty trivial, even to the optimizer, it will cache it for us, right?
Yes.
Okay, and second quick question is like, do you know anything on top of your head that the UL optimizer actually perform worse than the legacy optimizer, or it's like just like generally better?
It's an interesting question. So I have to add first, the UL code gen is significantly larger significantly more larger than the legacy code gen. So you really need to use an optimizer to like clean this like UL generated. So if the optimizer is not able to like clean up some of this giant code, then perhaps the legacy might be better. But again, benchmark.
Yeah, okay. Thank you very much.
No worries.
Hey there. In the latest Solidity release, the UL step is no longer stated as experimental on the documentation. Does that also hold for earlier versions of version 8 and version 7 set?
No, from 8.13, I think. Yeah.
So you wouldn't recommend using IR for V7 or V8.3 or something?
I mean, our recommendation is somewhat simple. Try to use the latest version as much as you can. Yeah.
But if there's an existing project that already has some other version, like I would still avoid recommending it, I guess. Is that the advice?
Going from, let's say, 0.80 to 0.813 is pretty trivial.
Yep.
But if you are below that, so you can actually look at the UL bugs from your version until 0.813, and if you think any of them are relevant for your project, then maybe don't use it. Otherwise, feel free to.
Sure. Thanks.
Hello. On your far right, do you ever foresee there being a future way for developers to reorder the dispatch table for popularly called functions?
Yeah, I think it's been a feature that gets requested quite often. We have an issue for it. Yeah, I think we could think about it again.
Hello.
Yeah.
Hi. So two questions. One about the fuzzer. Do I get it correctly that the fuzzer generates a big amount of possible valid contracts, and for each a big amount of inputs to then compare to the optimized version? So there's two steps. All right. Oh, mesmerizing.
Yeah, I mean, you try to generate contract and see if you can crash any of the compiler invariants. And then the second step is also provide it with some call data and try to see if the state is the same after the execution.
Okay, thanks. And do you have some benchmarks on numbers of what was the gas saving from some contracts that are now live that use this tool actually to do the optimization?
Right now, I don't have it, but I'm pretty sure we could find it. From my conversations with people, they who already use viaIR, they are finding it to be much cheaper than the legacy.
Thanks.